So welcome to our new video. So in this particular video we are going to derive the ground state energy for the delta potential using the variation principle. So we have used this particular variation principle to derive the same ground state energy for our harmonic oscillator, but today we are going to do it for the delta potential. So first of all we have to write out the potential of the delta potential. So the expression is V is equals to some constant alpha, and here is the Dirac delta function. So I have made a video on the delta potential in deriving whole of its energy using the solving Schrodinger wave equation and all that stuff for the ground state. So but in this particular video we are going to do it using the variation principle, which simplifies our problem because we don't have to solve the all of the Schrodinger wave equation to derive the energy state for the delta potential. That's why this variation principle is very important to derive the ground state energy, and it works well in some scenarios. So there is our potential for there is our Dirac delta potential. Here is alpha is a constant and there is a delta function here. Now next what we are going to do is, again we are going to derive out the expectation value of our kinetic energy and expectation value of our potential energy, because we have to finally construct a Hamiltonian. Then we will minimize our Hamiltonian with our parameter b that we will choose for our trial wave function. So that's why you have to construct first of all the expectation value of both these quantities, then it will sum up to form the expectation value of Hamiltonian. Then minimizing the Hamiltonian means we are finding this lowest energy expectation value, and that we are going to find out. So the expression for the kinetic energy will be same for our for our harmonic oscillator and for our delta potential, and which was h bar square b by 2m. This was the expectation. I'm not going to derive it. Okay, I have done it in the previous video, I guess, and this is I will borrow from the previous video. This is the expectation value for the kinetic energy. We are going to derive the expectation value for the potential energy. So remember as equation number 1. So expectation value of this was first and now second. So expectation value of potential is equals to, again, integration from I'm not putting down the limits because it will make this situation very unclear. That's why you have to assume that this integration is from negative to the positive infinity, and we have our psi complex conjugate, and here our the potential, which was the negative of alpha delta potential into psi into dx. So this was our expression. Now we are going to use the one of the principle. First of all, let me write down the value of our wave function, and the trial wave function that I am choosing is same as we have chosen for the harmonic oscillator, which is a e to the power minus bx square. So if we will do this, it will become a e to the power minus bx square, and negative of alpha here the Dirac delta function, and here again a e to the power negative bx square dx. Now if we will simplify this, it will become the potential is equals to the a square will come out of this, and also alpha negative, and integration of our e to the power minus bx square, and here delta function, and here e to the power minus bx square into dx. Okay, now our next will be ab minus a square integration e to the power minus 2bx square, and here psi of x and dx. Now if you remember one of the property of the delta function, because I'm assuming that you know about the delta function, the one of the property of the delta function was that when you will see this type of integral where there is a delta function and another ordinary function, it will look like this, that we are going to define our function, which is this our function at f equals, it means x equals to 0. This is the property of the delta function, that whenever there is a delta function in the integral sign and you have some sort of limits, then we have to choose your function at x is equals to 0. That's why it's represented as f of 0. So now if I will continue this, it will look like this, that this our expectation value of potential energy is equals to minus a square alpha, and this will become e to the power minus 2b x, and you have to put the value of x as 0, sorry, and minus, and you have to do this integration from negative infinity to the positive infinity of psi of x d psi of psi m, sorry, delta function and dx. And you know that this integral equals to 0 because the integral of these delta function from negative to the positive infinity is 0. Now you have defined your potential energy function as minus alpha, and this will become 1. And the amplitude, we have the formula of the amplitude as 1 minute, because we have derived this same amplitude in our previous video, as I'm writing it here, that amplitude is equals to 2b by pi 1 by 4. Okay, so when you do the square of this, you will find out at root under 2b by pi. So this is our expression for the potential energy. Okay, so this is our expression for potential energy. Now we are going to construct the Hamiltonian. Okay, so now we are going to construct a Hamiltonian, and the Hamiltonian will look like this, that Hamiltonian h bar square b by 2m minus alpha root under 2b by pi. Now if we have to minimize this, we will set as the differentiation of this particular Hamiltonian with respect to parameter b, and you will set that it's 0. And now it will like h bar square by 2m, and the derivative of b, it will become 1, and minus then alpha divided by root under pi, and d by dv of root under 2b, and it's equals to the 0. Now it will be like h bar square by 2m minus alpha by root under pi, and again root under 2 I will choose, and root under b by 2, which can be b1 by half, and differentiation will be equal to 1 by half into b1 by half minus 1, and equals to 0. Now h bar square by 2m minus alpha divided by root under 2 pi, because I will cut this out, and this will become root under 2 pi b is equals to 0. Now h bar square by 2m is equals to alpha divided by root under 2 pi b, and when I will shift this, it will become 2 pi b is equals to 2m alpha by h bar square, and when I will do the squaring on both sides, it will 2 pi b is equals to 4m square alpha square divided by h bar raised to the power 4, and the value of b that I am getting is m square alpha square divided by 2 and pi h bar 4. So this is the value of b I am getting. Now I am putting this particular value of b in our equation, which was Hamiltonian equation, which was h bar square, putting the value of b here, and divided by here it will be 2m into 2m square alpha square divided by pi h bar 4, and negative of alpha root under 2b by pi. Okay, I am gonna put the value of b here, which will be root under 2 into 2m square alpha square divided by pi square h bar raised to the power 4. Now if you will do this, it will be h is equals to 2 and 2 will cut out, this and this will cut out, you have m alpha square divided by h square, and minus alpha 2 alpha m alpha divided by pi h square. And if we'll do this, the Hamiltonian will be equal to m alpha square divided by h bar square minus 2 alpha square m divided by 1 minute. Here I have not written pi, sorry for this pi, and here with pi h bar square, and when you will take the LCM, it will be minus m alpha square divided by pi h bar square, and this is your lowest Hamiltonian for the delta potential, and this is our expression that we have to find out, m minus m alpha square divided by pi h bar square. So this expression is quite different. As I have said in my first video, that this is different because this is just an approximation, not the exact value. It will just do some of the approximations. It's higher than the ground state, but this method is quite useful in deriving the approximations of the Hamiltonian or the ground state of the different types of the system. So this is just an approximation, but very close to our exact value of the ground state. That's why variation principle is very important. So here I have derived all of the ground state energy for the delta potential. Now I'm giving you some homeworks. The homeworks were from the Griffiths. Yes, this is the particular question. So let me see. So this is your homework. So I have taken this question from the Griffiths quantum mechanics. So this is your question. As you can see that there's 2 star, it means it is quite difficult, and this is 1 star, as Griffith had mentioned in his preface that the 2 star are quite difficult, and the 1 star is quite easy. This is quite easy because in this particular question what he have done is that he has given the linear potential and the quartic potential. That's the only thing, but this is quite mathematical. Okay, but you know this is also doable. So these are the 2 homeworks that you have to do, and I will also make this video. I will also make a video on this particular topic because these questions are quite good to solve. So this is for today's video. Do this particular 2 questions, problem number 8.1 and problem number 8.2, and you will find the answers online, or I will make a video on that today or maybe tomorrow. So thanks for watching my video.